The Hubble Space Telescope orbits approximately 570 kilometers above the Earth, where it observes the universe free from the obstruction of our atmosphere. For nearly 3 decades, Hubble has studied the universe using its 2.4-meter primary mirror and its 5 science instruments. They observe primarily in the ultraviolet and visible parts of the spectrum, but also have some infrared capabilities. The electromagnetic waves in each of these bands have different characteristics, such as how they are produced and how they interact with matter and astronomical objects. Hubble observes in different wavelength bands, one band at a time, each providing different information on the object under study. Each of these wavelengths is reproduced in a different color, and these are combined to form a composite image, so that the contribution from all wavelengths can be compared and analyzed. For example, Hubble's images taken in the infrared typically reveal more stars than images taken in visible light, as infrared radiation passes more freely through cosmic dust, which scatters the bluer visible light. This allows astronomers to see regions of space that are normally obscured by cosmic dust and gas. By combining observations in different wavelengths, we can develop a more complete picture of the structure, composition, and behavior of an object than the visible wavelengths alone could ever show. While Hubble currently observes the universe primarily at visible and ultraviolet wavelengths, its scientific successor, the James Webb Space Telescope, will be sensitive to a range of wavelengths from 0.6 micrometers orange light to 28 micrometers deep infrared radiation emitted from objects at temperatures of about 150 degrees Celsius. More distant objects in the cosmos are more highly redshifted, and as a result, their light is pushed from ultraviolet and visible wavelengths into the near-infrared. This means that observations of these distant objects, for example the first galaxies that formed in the universe, require a telescope specialized for infrared observing, like James Webb, in order to be observed. The James Webb Space Telescope also has a much bigger mirror than Hubble. It measures 6.5 meters in diameter. Bigger mirrors collect more light from fainter and more distant objects in space, meaning that James Webb will be able to peer further back in time than Hubble, allowing us to develop our understanding of the early universe. Also, bigger mirrors provide higher resolution, resulting in images with finer details. By observing the cosmos in visible, ultraviolet, and infrared wavelengths, Hubble has contributed greatly to the field of astronomy. It has delved deeper into the early years of the universe than was ever thought possible, played a critical part in the discovery that the expansion of the universe is accelerating, and probed the atmospheres of planets around distant stars. We eagerly await the contributions and discoveries that James Webb will make in the future.